So now we have J.Mario Gallegos from Dell. He's Assistant Principal Engineer with Dell's High Performance Computing Engineering Division. In this role, Mario develops Dell HPC storage solutions with partners, and he currently provides technical consultation to customer executive teams for Dell HPC Lustre-based solutions. Mario joined Dell in 2007. He's working on HPC storage solutions since 2011. Previously, he worked in various roles for IBM and Sun Microsystems. Mario has more than 20 years' experience in research, Unix software development, software testing, systems integration, and solutions development. Ladies and gentlemen, Mario Gallegos.
Thank you, sir. Thank you, sir. Hello. Okay. So this presentation is about the proof of concept that we did right before supercomputing 2014, and it was to have Hadoop running on top of Lustre. And of course, the motivation is that the university had a new cluster, and they wanted to use it not only for regular HPC loads, but also for big data. And they wanted to share as much the resources as possible. They already have the compute power. They had the storage provided by Lustre, but they wanted to use those two with Hadoop. And well, typically, compute nodes don't have a lot of local space. In this particular case, they only have a space locally for the operating system. They have Hadoop and non-Hadoop applications that were going to share the resources, so they needed to have some POSIX compliance so they can use that storage. And they needed to use for Hadoop processes the MapReduce needed to access the storage efficiently. Also, the plan was to use 40 gigabit Ethernet, and we had to, due to the time when the decision was taken to do this, we only had 7 working days to do everything, from getting all the people involved, getting all the hardware, doing deployment, everything, testing, etc. So it was a little bit challenging because of that. This is the cluster that we're talking about. It's Cypress, ranked 271, and is based on Xeon Ivy Bridge and Xeon 5 processors, or coprocessors. And as I said, the idea was to do an effective combination of Hadoop running on top of Lustre. You could run Hadoop on top of Lustre using regular installation with the HDFS, but that's not very efficient. You're going to have a few problems, and you're going to also waste some data. We're going to talk about that a little bit. So Hadoop has 2 components, the MapReduce and the HDFS. What we really needed is the MapReduce, because HDFS is pretty much the same thing as Lustre, it's just a file system. So let's compare the two a little bit. We have on Lustre that computation shared data, while on HDFS data moves to the computation. On Lustre we have LNet to access data, while HDFS uses HTTP to move the data. Also, Lustre doesn't need data replication because it uses RAID or something similar to that to have some redundancy. In HDFS uses copies, so you have data replications. Typically, you have 3 copies of your data distributed among the different nodes. Lustre is centralized storage, while HDFS is local to the compute nodes. Lustre is POSIX compliance, HDFS is not. Lustre is widely used for HPC applications, and HDFS is widely used for MapReduce applications. On Lustre, all of your data is available at any point in time, and on HDFS, your data kind of is used during the shuffle MapReduce phase, and you may need to migrate it. Another additional benefit of Lustre is that you can back up or recover your data using existing infrastructure, like HSM. So the integration of the regular HPC loads and the big data required to have MapReduce added. We didn't know in advance what was the mix of Hadoop applications, big data applications, and regular HPC. It could be from multiple fields. It's guaranteed to change over time. So we needed to be very careful about what was used. Also, since the workloads run differently, you use different schedulers for Hadoop and for HPC. And we needed as much as possible to run the MapReduce workloads just like HPC workloads. And using Hadoop and using Lustre also implied, in this particular case, that they needed to either train or hire admins for managing Hadoop and Lustre. So if we could simplify or automate as is, whatever we could do to minimize that, that was very welcome for this project. And because of the time constraint, we had to rely heavily not only on our partners, but also on the products that we already have, so we could meet the deadline. The hardware was the first problem. We didn't have time to order anything, so we had to appropriate a system that we were using for Lustre training. And we decided to have everything ready and ship it. So the system was racking, the rack was racked with wheels, so we could move it easily. Everything was cable deployed, tested, and then we shipped it to the site, to Tulane University. The plan was to use, as I mentioned, 40 gigabit Ethernet and add Hadoop support on once we were on site. And in addition, just in case, we sent a box full of all the cables that we assumed we could need, extra adapters, tools, etc. Anything that we foresaw we could use, we sent. In terms of partners, we decided to go with Intel for a couple of reasons. First and foremost, we already had a solution with them based on Intel Enterprise Edition for Lustre. They have already a component that allowed to efficiently replace HDFS, and also they have plans to have a replacement for Yarn, for the scheduler that Hadoop normally use. So those were the main criteria. And now for integrating this with a cluster, we started to use RIDE for a few reasons. The main one is they already were used for this cluster. So Cypress is already using RIDE for management. It supports Cloudera distribution of Hadoop. And it allows also to do the deployment of Lustre clients, where we have that support working. So having all those components was going to make easier this project. Now the hardware that we decided to use is, as I mentioned, based on a system that we already have for training purposes. It's based on the R620, which uses Ivy Bridge processors, 2 of them, 128 gigs of DDR3, 1866 mega transactions per second. Sorry. We have all of the servers were exactly the same in terms of those items. That was on purpose, so we can exchange servers if needed, and that proved to be very useful later. We had on the management server, pretty much just a management connection based on Ethernet. On the metadata servers, we have 2 of them on an active-passive pair. a single MDT based on the Powervault MD3220 with 24 SAS 15K RPM drives, 300 gigabytes each. We were using a RAID 10 with 22 disks and 2 spare disks. The server, excuse me, the servers had a 6 gigabit per second connection to each of the controllers. This particular storage has 2 controllers, RAID controllers. So each server had a connection, SAS connection to each of the controllers. And for the object storage, we have the same servers, but this time they were connected to Powervault's MD3260s. Again, using SAS links of 6 gigabits per second. In this case, we had 4 controllers, so we have 4 connections from each server connecting all of the controllers. And initially, we only had those 2 arrays, but if needed, we had the option to appropriate more hardware and expand the file system with 2 MD3060Es. At the end, that was not done, but that was an option that we had. Send those later and integrate them. So once we had that, the plan was just to get the rack in place, connect the 40 gigabit links, and then since Cypress already had head nodes with RAID 7, we just needed to add support for the Cloudera distribution of Hadoop and the plugin that Intel provides to handle Hadoop efficiently. And I'll talk more about that. The thing about that plugin is, as I mentioned, it replaces HDFS efficiently because it allows Hadoop to interact directly with Lustre. Well, it's a jar, a library file that already allows connecting with Lustre. It avoids having the multiple copies of the data, so it's what they call null shuffle and 0 copies. And it's easily deployable. We didn't need to make any major changes to the configuration of Hadoop. And there was no changes needed to the way the jobs for Hadoop were done. So we still needed to use Yarn, but we didn't need to modify anything. And it was already part of Intel Enterprise Edition for Lustre. Now, as I mentioned, another thing that we consider is that Intel had in the plans to replace Yarn with another scheduler based on Slurm. And Slurm is widely used, so that was a good thing. That way, once that was completed, Tulane could use the same scheduler for both big data applications and regular HPC applications. It didn't require modification to Hadoop, enable all the applications to execute without modifications, maintain license separation, is fully transparent to the sharing of the resources. And well, Intel also mentioned that improves performance. That's yet to be tried once the real system is implemented with the version of IEL that supports that. And the way that the Hadoop can run with Lustre is that it uses the built-in local file system class to add Lustre supports. By extending and overriding the file behavior of this class in defining a new scheme, URL scheme for Lustre. It allows to control Lustre striping information, resolves absolute paths to directories, helps to optimize the shuffle phase, which should translate in performance improvements. And on the nodes, as I mentioned, RAID 7 was already used to do the provisioning of the 124 nodes. And with this in mind, we could use it to also deploy whatever number of Hadoop nodes were needed. We were assigned 8 nodes just to do the proof of concept. And we use it to deploy the Cloudera distribution of Hadoop. on these nodes without the HDFS. We use also the Bright software to deploy Lustre on them in the HAL component. Excuse me. So once we had that working, the Hadoop Notes could access Lustre directly. If needed, we could change the mix of Hadoop Nodes and HPC nodes very, very fast. We had an image for each of them, so it was very easy to do the redeployment. Now, we have quite a bit of challenges that were briefly mentioned, like we only had 5 days to do everything on site. And even that we sent the system, the Lustre system, fully installed, working, and tested. The first problem is it didn't arrive on time. It arrived 1 day late. And then once we arrived on site, we found out that the location for that system was too far away from the cluster. So we didn't have cables long enough for 40 gigabit Ethernet. And we were trying to get those when we decided to check the switch. And the big surprise is there was only one port open for our system, and we needed 4. One for each of the system, 2 OSS, 2 MDS servers. So another big issue that we couldn't work around because they needed to have also Cypress ready for supercomputing. So the solution was using a breakout cable and replace our interfaces with 10 gigabit, which was going to limit the maximum throughput. But we configured the port, and we used that cable. Everything was supposedly working, and then when we were testing again Lustre, surprise, the iDRAC was not working on one of the metadata servers, and we used that to enforce node eviction. So if a server is having problems, we use the iDRAC to shut it down. We sent another system from our lab, but that was going to take another day, so we decided to just swap the management server that doesn't need the iDRAC in this machine, and then redeploy Lustre. So just minor set of setbacks that we had to work around. So once those issues, well, actually in parallel to some of those issues, we started to have people from Intel and Bright working on doing the integration of IEL in Cloudera, the plugin in Bright. And that was good because parallelizing all those efforts, we saved some time. Since the performance was going to be limited by the 2 links that we had to the OSS, the maximum performance that we were expecting to get was 2 gigabytes per second. So we focused more on demonstrating the feasibility. We didn't try to optimize things. And we were going just to show that it can be done. It was easy to administer, to monitor. And we did some performance just to show that it was good enough, even that we have that restriction. As I mentioned, doing the parallelization of the different things that we needed to be done allow us to complete everything in 4 days instead of 5. And actually, the last day was minimal what we did. So that was good. But also Tulane University staff and executives were very supportive and allow us to overcome most of the problems that we had. Now, in terms of performance, I already mentioned the limit on the performance. So using DFS I/O reported 134.91 megabytes per second, and that was using 12 files of 122,880 megabytes each. So if you do the math, that's about 1,619. And IEL was reporting 1.6 gigabytes per second. So we're within 80% of the maximum throughput, maximum possible throughput, without any optimization. Not too bad. We also ran Terra Sort and got these results. And for that means at Tulane, the GUIs that are provided by Bright and the IML GUIs were also another benefit. For example, here, this is showing one of the metrics that Bright can display. It's like a heat map that allows them to see how a Hadoop job was using resources over time. So in terms of the lessons learned of the deployment, again, this more than technical is just about what we face with the restrictions that we have. Allocating in advance the people, the correct people, and enough people to handle the project was very, very important. Without having everybody available at the time, we wouldn't be able to finish. Also, our partners gave us full support, and that allows this to happen. The reuse of existing technology saved a lot of time. A few things that we needed to do different if this happens to come again as a very short notice project is gather in advance all possible information about the equipment, the power, networks, anything that is needed for your system. Get an agreement in advance about the location of the systems, using whatever means necessary to clarify points. And also consider that since Murphy never takes a break, hardware can fail at any time, even if you just test it. Try to be prepared for things like that. Also getting in advance access to the different accounts or lab or whatever is needed is, it can save time. In this situation, it was not very important because since we didn't have the hardware on time, the first day was just to get this type of access. But that's something they could have done in advance and save even more time. Also, we had people in Tulane, which is in New Orleans. We had people in Austin, and we had people in France. I don't remember exactly what city in France. So using conference calls, setting up remote access to all the different people that were involved was extremely important. And since we have a big disparity in time zones with the people in France and the people in New Orleans and Austin, we have to be very flexible. So we were working weird hours sometimes, especially the first few days to make sure that everything could be completed on time. Another important part was the decision of using the same hardware for the servers, because that allows us to replace the server that was having problems. And the division of assignments based on competence in getting remote support from other coworkers was priceless. Another useful thing was to have a single chain of command so that we didn't have any contradictions, providing frequent status to all the people involved. So communicate, communicate, communicate is gold. I want to acknowledge the different people from Dell, Intel, Bright, and Lustre that helped us to make this possible, in addition to the people that were already listed as part of this presentation. Any questions?